How many people need to show up for your party before you have two with the same birth date? The experts know one answer, but there's another one that has them stumped. Perhaps you will be the one to figure it out. You have 23 people at your party. The odds are just slightly better than 50-50 that two people have the same birthday. This is a well-known amazing fact that you might have already heard about. But there's a bizarre twist to this story, where it appears that it might actually require 25 people, depending on how you let them in the door. Let's use Python to see if we can figure this out. First, let's experiment with a program that supports the theory that a party with 23 people will have at least two people with the same birthday, slightly more than half the time. A Monte Carlo simulation works great to test this. Here's the code. I'll talk through it so it's clear how it works. Any Monte Carlo simulation requires lots of random numbers, so our first line imports the random module. We set up 4 variables. The first one is the number of parties we'll simulate. Each party will have 23 guests. Feel free to try different numbers of parties and guests to see how 23 is the magic number where the odds of two people having the same birthday just barely goes over 50-50. The variable named duplicates will count up the total number of parties, out of all the thousands of parties we try, where we get one or more duplicate birth dates among the guests. Birth dates is a list containing 365 integers, from 0 to 364. Think of these as each day of the year. In reality, years have slightly more than 365 days on the average, but the slight difference doesn't matter. And we'll use the same range of birth dates in both programs. Once those variables are set up, we loop through all the parties, one at a time. Guest birthdays is another list that is built from scratch for each party. Random.choices is an interesting function that selects k-samples from a list. In this case, we select 23 birthdays from the list of all possible birth dates, and these 23 dates fill the guest birthdays list. Notice that the choices function can select with repeats, so randomly every once in a while it will select the same number more than once as it builds the guest birthdays list. The next if line is really cool, as it shows how Python can often do amazing things in short lines of code. We convert the guest birthdays list we just created into a set. Recall that a set has no duplicate items, so if there are two, or more, identical items in the guest birthdays list, all the duplicates get eliminated. The len function tells us if the set is shorter than the original list, in which case there were duplicate birth dates. If the set is still 23 long, then there were no duplicates. For each party where there were duplicate birthdays, we increment the duplicates count. Finally, after all the thousands of parties have been simulated, we print the number of parties with duplicates by the number of parties. Run this program multiple times, or for a large number of parties, and you'll see that it always averages out to approximately 0.507, or slightly more than half of the parties have two or more partygoers with the same birth date. Now we get to the bizarre second program. In the first program, we let 23 people in the door to fill the party, then we checked all their birth dates all at once. In the next program, we'll let people in the door one at a time, and immediately check to see if any of the partygoers already in the room match this new partygoer's birth date. If so, we stop there and tally how many people are in the party, send everyone home, and start over with the next party. Here's how the code works. We import the same random module, and we simulate thousands of parties, just like before. The total guests variable will add up all the people we let in the door for all the parties. For each party, we start by creating an empty guest birthdays list. As we open the door to let a guest in, we append their randomly selected birth date to the list. The if test checks to see if this new partygoer happens to have the same birth date as any of the previous people we let in the door. Notice we're checking to see if this freshly added birth date at the end of the list is matched with any of the other previous items in the list, not including the last item in the list, hence the -1 in the list slicing. If there is a duplicate birthday in the list, the break command kind of shuts the door and doesn't allow anyone else to come to the party. The number of people in this party is then added to the total, everyone goes home, and we start checking the next party. Finally, after all the thousands of these bizarre parties are done, we calculate the average number of people we had to let in the door for each party, by dividing the total number of guests let in the door for all the parties by the number of parties. That should result in the average number of partygoers required to find duplicate birth dates. I fully expected this result to be slightly less than 23 people per party, to match the results from the first program. But, as you'll see when you experiment with this program, it takes approximately 24.6 party people in the door, on the average, to find a duplicate birth date. If you think about it, this means if we always let in only 24 people, we'll get duplicate birthdays less than half the time, so we need to let 25 people in one at a time to get duplicate birthdays slightly more than half the time. To summarize, with the first program we get the answer agreed upon by all the experts. It takes 23 people to discover a duplicate birthday slightly more than half the time. In the second program, we have to let in 25 people one at a time, on the average, until we discover a duplicate birth date. I'm confident there's a simple logical explanation for this discrepancy between the two programs, but I have yet to figure it out, even though I've had a lot of fun experimenting with these two programs and showing them to my friends. Okay, there you have it, today's birthday surprise Python Playground challenge. If you can explain this mysterious result in a clear and understandable way, please let me know. I'll be sure to share the best explanation in a future episode. If you enjoy real-world, useful, and understandable Python examples and challenges as a way to learn, keep fresh with your programming skills, and just to have fun sharing with your friends, you know what to do. Like and subscribe. Thank you so much, and have fun.